Random variables are the basic objects of probability theory. In this class, we'll be dealing with both discrete and continuous random variables. Discrete random variables take values in a discrete set, like, for example, the outcome of a coin flip, or of a roll of a six-sided die, but could also be infinite, like, for example, the number of times it takes me to flip a coin before I see a heads. Continuous random variables take the values in a continuous set, which will often be a subset of the real line, like, for example, if my random variable is a uniform number between 0 and 1, or if it's the amount of time I wait for the bus. But it could also be an element of a higher dimensional space, like, for example, a uniformly random element in the unit square. You can specify a discrete random variable by writing down the probabilities of all its outcomes. Like if x is a fair coin, and y is a sequence of two fair coins, and z is the roll of a fair six-sided die, then I can specify all of these random variables like this. The probability mass function of a random variable is the function mapping outcomes to the probabilities of those outcomes. This is just a different notation for the same information expressed before. You can also specify discrete random variables by writing them as a function of other discrete random variables. For example, let x be a sequence of 10 independent fair coins. I'm not going to write down all the probabilities because there are more than 1,000 possible outcomes, but in principle you could. Now let y be the number of consecutive heads at the beginning of x, and let z be the number of heads in x. Y and z are random variables that I've defined by expressing them in terms of another random variable, namely x. To test your understanding, try writing down the probability mass functions of y and z.